Hello, everybody. I wanted to make this video as kind of some supplemental notes to the Fourier series, and this is specifically for anyone who chooses to do the thermal waves experiment in the PHYS 232 lab. Um, first off, I guess we should maybe review what is the goal or what's the objective of Fourier series. And so, what I want to imagine is a periodic function. So, I'll plot some function of x, and this f of x is periodic in x. And so, it doesn't really matter what it looks like as long as it's periodic. And so, I can't draw it perfectly, but you get the point. And so, it'll be periodic for these negative times as well, or negative values of x. Um, so if you were doing a physics lab, you might be looking at an electrical signal on an oscilloscope, and it could be periodic and have some strange shape. So what a Fourier series attempts to do is to express that function as a constant plus a sum of sinusoidal and cosine terms. And so it would look like A0 is our constant offset. And then there's an A1 term times cos of x plus A2 times cos of 2x plus A3 cos of 3x plus and so on. Plus a B1 coefficient times sine of x plus a B2 sine 2x plus b3 sine 3x plus and so on. And so, of course, we could write this a little more nicely by saying this is a0 plus the sum from n equals 1 to infinity of an cos nx plus the sum, say, from m equals 1 to infinity of bm sine mx. And so what is the advantage of doing this? Like, let's suppose it's possible. Why would we want to do that? So if you're thinking about a periodic function in time, if we were able to break it down as a Fourier series in the way it's expressed here, then we could look at the various terms in the series and we could say, well, there are terms of a different frequency. So here is what we might call the fundamental frequency. It's the period of the signal. And so here, let's assume that this signal that we're looking at is periodic on minus pi x to pi. And then here, there's a signal of twice that frequency, 3 times the frequency, and then we have the cosine and the sine terms. And it goes on and on and on. So what we could look at are which terms in the series have non-zero coefficients, like which of the A1 or A2 or A3 or any of the AN, which ones are non-zero. That tells us the frequency content of the signal as well as the B1 coefficients, the Bn coefficients. And so we could look at the non-zero coefficients, and that would tell us what frequencies are present in our actual signal. And then we could look at the coefficients of those non-zero terms, and we could tell what are the relative contributions of each of the frequency components that make up our signal in time. So when we look at the thermal waves data, what we're really going to be looking at is how does the coefficient of, it'll turn out to be this coefficient, how does this coefficient change as we move away from a heater that's being turned off and on periodically? And so we'll want to be able to do some kind of Fourier analysis of the data that we collect and then look at the height of this term, which is determined by the B1 coefficient. Okay, so that's a bit of a motivation for why we might want to do that. Before we go and do these calculations, what we need to do is we need to cover some preliminaries. So, preliminaries. The whole goal of what we're going to do is we're going to try to find out a way of determining the values of the coefficients A0, AN, and BM. Okay, so we'll assume that it is possible to write a periodic function in the way that's expressed here in equation 1. And if that's possible, then we need to determine all those coefficients. And it will turn out, as you'll see soon, that we'll have some integrals to evaluate. And so there's some useful things for us to have in our back pocket before we go and tackle this problem. The first thing I want to consider is the integral from minus pi to plus pi of sine nx times sine mx. And we'll assume that n and m are integers one or greater. And so maybe we should say n is greater than or equal to 1 and m is greater than or equal to 1. Okay, there's a couple ways that we could tackle this integral. We could write sine in terms of its complex exponential. So sine of nx would be e to the inx minus e to the minus inx, all divided by 2i. And then we could try to do that integral, and it would be relatively easy or straightforward because integrating exponentials is quite easy. Another way, which we'll do here, is we'll rewrite this product of signs using a trig identity. And so the trig identity will allow us to write this integrand as minus 1/2 of cos m plus n minus cos of m minus n. Sorry, I forgot an x. There should be an x right here. X minus cos of m minus n x. And then we integrate with respect to x. Okay, so if we consider now the case of, we're going to have to consider two cases. Case 1, which we'll start with, is that m is not equal to n. Okay, so when we do the integral, we'll get a minus 1/2, and then let's see, we'll get a 1 over m plus n. The integral of cos is plus sine, so we get sine of m plus n x evaluated between minus pi and pi. And then we get minus 1 over m minus n sine of m minus n x evaluated between minus pi and pi. Okay, you can see why we have to consider the m not equal n case separately from m equals n, because when we have m equals n, we'll have a 1 over 0 here, which would be a problem. So we'll have to consider that case separately. We're basically done here, because if m and n are integers, then sine of an integer times pi is always 0, and sine times an integer, sine of an integer times minus pi is also always 0, and so what we get here is 0 and 0, and this first case tells us that the integral that we're trying to solve, which is sine nx times sine mx integrated between minus pi and pi, is 0 for this case 1 where m and n are not equal to one another. Okay, so case 2 is I is going to be equal to, maybe what we'll do is we'll go back to this expression and we'll just say, well, what if we said m was equal to n? Well, we would have a minus 1/2 the integral from minus pi to pi of cos 2nx minus, and so now we have m is equal to n, so m minus n is 0, but cos of 0 is just 1, so we have a minus 1. And so this is equal to minus 1/2 of, let's see, 1 over 2n sine 2nx minus pi to pi. And then when we integrate 1, we'll get an x evaluated between pi and minus pi is 2 pi. There's a minus sign out front, so we get minus 2 pi. Like before, this first term is going to vanish because sine of 2n pi and sine of minus 2n pi are both 0. And so we have minus 1/2 times minus 2 pi, and so this is equal to pi. So what we can conclude from this then is that the integral from minus pi to pi of sine nx sine mx is equal to 0 when n is not equal to m, and it's equal to pi when n is equal to m. Okay, and again, I won't write it down again, but we're assuming that n and m are positive non-zero integers. Okay, so I'm going to leave it as an exercise for you to show that the integral of cos nx times cos mx from minus pi to pi has the exact same outcome. It's 0 when n and m are not equal, and it's pi when n is equal to m. And there's a third one, and that is cos nx times sine of mx, and that is going to be equal to 0 for both cases, for all n and m positive integers. It doesn't matter if they're equal or not equal. Okay, so let's get back to our Fourier series, which is right here. I think I'm going to write it out again, and then we're going to make use of some of these results that we've written down. Okay, so the Fourier series. It says that if you have a periodic function f of x, so periodic on minus pi to pi, then that function, no matter what it is, can be expressed as a0 plus a1 cos x plus a2 cos 2x plus a3 cos 3x, and this just keeps going, plus b1 sine x plus b2 sine 2x plus b3 sine 3x, and so on. Okay, so the problem here is that we have an infinite number of coefficients to determine. If this assertion is true, we have to determine a1, a2, a3, b1, b2, b3, all the way out to infinity for both of those, plus the a0 that's out front. So the first thing we're going to do is we're going to try to integrate this f of x. So let's take f of x, which is periodic on the interval minus pi to pi, and let's just integrate the thing over that interval. So what we would get is an a0 integrated from minus pi to pi dx plus a1. Well, let's just do an integrated from minus pi to pi of cos nx dx. Actually, let me rewrite this. So it would be plus the sum from n equals 1 to infinity of an, the integral of minus pi to plus pi of cos nx dx plus the sum of m equals 1 to infinity of bm from minus pi to pi of sine mx dx. Okay, so we have three integrals to evaluate, and what we're going to get is a0 times 2 pi plus the sum from n equals 1 to infinity an 1 over n sine nx from minus pi to pi. Sine of n times pi and sine of minus n times pi, that's always 0, plus sum of m equals 1 to infinity of bm 1 over m cos mx, and I think we're going to pick up a minus sign from minus pi to pi. But because cosine is an even function, cos of, well, let's write this out. This is cos of m pi minus cos of minus m pi. But cos is an even function, so this is cos of m pi minus cos of m pi, and that's equal to 0. So the only thing that survives from this entire integral is the very first term, which evaluates to 2 pi times a0. And so therefore, we can deduce that a0 must be equal to 1 over 2 pi, the integral from minus pi to pi of f of x dx. Oh, sorry. Let's get that back. What have I done? Okay, here we go. Got it back. All right, so we have our very first coefficient. We still have to find all of the other an and bm for n equals 1 to infinity and m equals 1 to infinity. But it turns out it's not so difficult. So what we're going to do is we're going to try another integral of f of x when it's expressed as this Fourier series. And so next we're going to try to evaluate the integral from minus pi to pi of f of x times cos of nx dx. Okay, and so the f of x is going to be, well, it's going to be an a0 times minus pi to pi of cos nx dx. And I think we can already see that this cos is going to integrate to a sine, and the sine of pi and sine of minus pi is going to vanish. So this already we can see is going to be 0. And then instead of writing this out as in the summation notation, I'll just write it out term by term. So we'd have an a1 integral from minus pi to pi of cos x times cos nx dx. But now we're going to go back to these integrals that we determined here, and we're going to use this one. It says that the integral of two cosine functions is always 0 unless the n and the m are equal. Well, over here, if we assume n is not equal to 1, then the coefficients in front of these x's inside the cosines are not equal, and this is going to be 0. And then we'd go to a2, we'd have integral from minus pi to pi of cos 2x cos nx dx. And so this is like an m equals 2 and an n, let's say, not equal to 2, and that's going to vanish. And we'd have a whole bunch of more vanishing terms until we finally got to the n coefficient. So we'd have an from minus pi to pi of cos nx times cos nx dx. And if we remember, when n and m are equal, that evaluates to pi. And so all of this is going to be pi. And then we'd have like cos n plus 1 times x times cos nx, and that would integrate to 0. And this is the only term that survives in the cosine series. But then we also have to look at the b1 integrated from minus 1 to 1 of sine x cos nx dx plus b2, the integral from minus pi to pi sine 2x times cos nx dx, and a bunch of other terms. And so now we have the sines and the cosines mixed, and by this identity, it doesn't matter what the n and m values are. When you mix the cosine and the sines, it always integrates to 0. And so this is going to be 0, and this is going to be 0, and all of the other b terms are going to be 0. And therefore what we get is that the integral from minus pi to pi of f of x cos nx is equal to pi times an, or what we're really trying to do is determine these a coefficients. We then have a general expression for an when n is 1, 2, 3, 4, 5, 6 up to infinity. It's equal to 1 over pi, the integral from minus pi to pi of f of x cos nx dx. Okay, and so now what we've determined is the a0 coefficient and the an coefficient. I'm going to leave it as an exercise. Show that the bm coefficient is, you could probably guess what it is. It's 1 over pi, the integral from minus pi to pi, f of x, not times cos of nx, but times the sine of mx dx. The way you would prove that is very analogous to how we just did it for the an coefficients, except this time what you're going to have to make use of is this result here, this first one, that we actually proved the sine nx times sine mx results. And then you'll also have to make use of this last one that mixes the cosines and the sines. Okay, so let's just summarize all of the important results. Summary. So the Fourier series can be used to express periodic functions as sums of cosine and sine terms. And the way it looks is f of x is equal to a0 plus the sum of n equals 1 to infinity of an cosine nx plus the sum of m equals 1 to infinity bm sine mx. This is for this case that we've written down here, where f of x is periodic on minus pi to plus pi. Okay, so the coefficients are determined from, let's see, a0 was 1 over 2 pi of the integral from minus pi to pi of f of x dx. An was equal to 1 over pi of the integral times the integral of minus pi to pi of f of x cos nx, and bm was 1 over pi times the integral from minus pi to pi of f of x sine mx dx. Okay, so this is the big summary here. And so what I want to do is I just want to go through an example to show you how this works. And this example is actually relevant to the thermal waves lab, where we're going to have a heater being turned off and on periodically. And so that's like applying a square wave to the heater. So when the square wave is high, the heater's on. When it's low, the heater's off. And in the thermal waves experiment, what you do is you look at how the resulting temperature oscillations change as you move away from the heater. Okay, so let's work out that example. So example is, let's say example, a square wave. So we'll make a square wave that's periodic on minus pi to pi. So it'll look something like this. Here's f of x, which is going to be our square wave. Oh no, not this again. Okay. Okay. So what we'll do is we'll have the square wave be high, and then low and high, and low and high, low and high, and so on. And then it'll also go to negative x values. Something like that. Okay, so this is +1, and this is -1. Here is pi and 2 pi and so on. Here's 0, minus pi, minus 2 pi, and so on. Okay, and so what we need to do is we need to find our A0 coefficient. And we have an example where this is actually pretty straightforward to do. On minus pi to 0, our function is equal to -1. And on 0 to pi, our function is equal to +1. And so that means all we need to do is separate our integral into two parts. I guess it's a piecewise smooth integral. So we'd have 1 over 2 pi, and then we could integrate from minus pi to 0. And on that interval, f of x is just equal to -1. And then we would integrate from 0 to pi. And on that interval, f of x is just equal to +1. Okay, so that's equal to 1 over 2 pi times, let's see, we'd get minus x from, I don't want to make a sign error, so I'm going to write this out a little bit. And then this would be x from 0 to pi. Okay, so this is 1 over 2 pi, and then it's, let's see, minus 0, and then it would be plus minus pi. So I think it's like that, and then we would get plus pi minus 0. And so what we end up with is minus pi plus pi, and so that's equal to 0. Okay, good. Now, an is 1 over 2 pi, the integral from minus pi to pi of f of x cos nx dx. And what we're going to do is the exact same thing. So I made a mistake here. For this coefficient, we just have a 1 over pi out front. Okay, but we're going to break the integral up into two parts. So it would be from minus pi to 0, and then on that interval, f of x is minus 1. So we have minus cos nx dx plus the integral from 0 to pi times f of x is going to be plus 1 cos nx dx. Okay, so it's 1 over pi. You might already see what the result is going to be, but let's just work it out in a little bit of detail at least. So when we integrate cos, we get sine plus 1 over n sine nx 0 to pi. Okay, but for integer n, well, first of all, sine of 0 is 0, and for integer n, sine of n times pi or sine of minus n times pi is always going to be 0, no matter what n is, as long as it's integer. And so that means all of this just vanishes, and so this is 0. So what we found so far is for our square wave, a0 equals 0 and an equals 0 for all n greater than or equal to 1. Okay, so we better hope that some of our BM coefficients are non-zero, otherwise we're not going to have any terms in our Fourier series. So let's see what happens. BM is equal to 1 over pi, integral from minus pi to pi of f of x sine mx dx. And it's just the same game. We separate our integral into the two intervals. We get minus sine mx dx plus the integral from 0 to pi of sine mx dx. Okay. Now let's see. When we integrate a sine, it becomes minus cos. So we just have to keep track of the negative signs. So we get a 1 over m cos mx from minus pi to 0. Then I think we're going to pick up a minus 1 over m cos mx from 0 to pi. Okay. 1 over pi. Let's just factor out the m. And then what do we have? We have cos of 0 minus cos of minus m pi minus cos of m pi, and then I guess we'll get a plus cos of 0. Okay, cos of 0 is 1, so we have a 1 plus 1, which is 2. Cosine, again, we've used this result before as an even function. So cos of minus m pi is just cos of m pi. And so what we end up with, I think, is 1 plus 1 is 2 minus cos m pi minus cos m pi is minus 2 cos m pi. So we can factor out a 2 pi times m, and then we have a 1 minus cos m pi. So these are our Bm coefficients. All right, so we could make a table and our table could be m cos m pi and 1 minus cos m pi. So when m is 1, cos of m pi becomes cos of pi, which is minus 1, and 1 minus minus 1 is 2. When m is 2, we get cos of 2 pi, that's plus 1, and 1 minus 1 is 0. 3 is cos of 3 pi, which is minus 1, and we get a 2. 4 is cos of 2 pi, that's a plus 1, and we get a 0. And you can see what's going to happen is that we get non-zero results for odd values of m, and we get 0 for even values of m. Okay. Now, when m is odd, we get a factor of 2 here. So this becomes 2 for m odd and 0 for m even. So what we could write then is therefore Bm is equal to, let's see, when it's odd we have 2 times 2, it's 4 over pi times m for m odd, and it's 0 for n even. All right, good. So then we can write down our full Fourier series. For the Fourier series for our square wave is therefore a0 is 0, all an are 0, so there's no cosine terms. We have just the sine terms and only the odd ones. They're all going to have a 4 pi out front, so we could have a 4 pi, and then when we have m equals 1, we get sine x, and then m equals 2 is nothing because that's an even term, so then we have a 1/3 for the 1 over m here, sine 3x plus 1/5 sine 5x plus 1/7 sine 7x plus and so on. And so that is the result of the Fourier series of a square wave. And you might look at that and you might understandably think, well, how do I know that that actually looks like a square wave? It doesn't seem like, at first glance, that it would look like a square wave. So I've generated a plot here that I want to show you. I'll generate some plots. They're actually on the course website. So here we are on the course website, and I just want to scroll down to course materials. And so here's a January 17th entry, and there's an example of constructing periodic square wave from a Fourier series. Okay, so these plots were made in Maple, and what you can see is that we have a coefficient of 4 over pi right here, and then times sine x. So this is keeping just a single term in the Fourier series. And of course, you know, that just looks like a sine wave. It doesn't look like a square wave at all. So then what we do is we go and we add in a second term. So we have our sine x plus 1/3 of sine 3x. And I mean, you can already start to see that it's looking more like our square wave. It definitely is not a great square wave, but it's starting to pick up that shape. And here we include the 1/5 plus sine 5x, and it starts to look a bit better. Here's the 1/7 plus sine 7x. And then here I just added a whole bunch together quickly. So it's all the odd terms up to m equals 29. And so the highest order term is 1 over 29 plus times sine of 29 times x. And so that's a pretty good square wave. There are some oscillations at the horizontal parts. But anyways, I'm going to show you some more. But these are just all of the plots together, and you can see that evolution towards something that looks more and more like a square wave. So here is, I wrote a loop in Maple to sum all of the Fourier terms for our square wave up to m equals 5001. Now, of course, it's keeping only the odd terms in that sum, and so there's probably about 2,500 terms in this sum. And when I plot it, you can see that those oscillations in the horizontal sections are suppressed. You can see some imperfections right where it has to transition from being vertical to horizontal. But if you could actually write down and include all infinity of those terms, then this would converge to a perfect square wave. So anyways, that's an introduction to Fourier series, and it'll give you hopefully a bit of a better understanding of what you're doing when you're doing the analysis, the Fourier analysis of the thermal waves data that you collect, if you choose to do that experiment. All right, great. So thanks very much. That's where I'm going to end this video, and I'll see you later.